So for formally, we're going to look at what happens at infinity, right? So we've talked about it a lot, but as x goes to some number from the left or right, or just some number in general. But now we're looking at infinity. So you're really looking at the very end of the graphs. And it could be infinity or negative infinity, right? So you're just thinking, well, what in general does a graph look like? So a good way to think about this is actually, before we get into more difficult graphs, is what happens for something like a parabola as x goes to infinity. Right? So this graph, which is x squared, as x goes to infinity, of x squared, right? You're just asking, really just saying, forget all this stuff. I don't care about what's happening at 0, 1, 2, 3, 4. We're talking about infinity. What happens, when we get to a really, really big number? We have to imagine what happens way out there. And we already know that this graph just keeps on going up and up forever. So this, right, will just go to infinity, just like that. Okay. So we don't really say infinity, though. We say it does not exist. But you want to keep those two closely linked together. So it's not that it goes to infinity necessarily. It might just not exist at all. Okay. Same thing if this is going to, if I just throw a little negative on here. Then we're looking over on this side, what's happening at the graph over here. Well, that's also going to infinity, so it does not exist, right? So we want to think about, what the graph looks like in general. And of course, if this was a negative x squared, right, then this would be heading to negative infinity. So just knowing in general what happens with graphs when you put negatives in front of them, right, negative x squared, that will help us as well. So the more you can visualize the graphs, the easier it is to do this, and the less mechanical it becomes. Now we have all these algebraic ways of doing things because a long time ago we didn't have Desmos or graphing calculators, and you had to have a algebraic way of figuring out answers because it would take way too long to graph these things by hand. So you guys have the benefit of saying, well, I could just look at the graph and see if it has this horizontal asymptote from the bottom, right, and approaches some limit from the top or the bottom, right? So in this case, this is where we would have limits that actually exist. So we're just looking for, does it get closer and closer to some number on this axis, right, as we get bigger and bigger and bigger on the x-axis. So in this case, that's where the limit would actually exist, right? So this is what converging, right, which means the limit does exist. All right, just getting closer and closer. That's if you have a graph. If you don't have a graph, maybe it's something like this where you can already know what it looks like, whether it's x squared, x cubed, even log of x, even power functions, sine of x, cosine of x. We know what these graphs look like in general. All right, so sometimes we can come up with it. And the limit does exist, and that answer is whatever L is, right? That's what we're looking for. And then we have the other case, maybe like a power function that just kind of goes up and up, like 3 to the x, or 3 to the 1, 3 to the 2, 3 to 3, 3. It just infinitely gets bigger and bigger and bigger. Therefore, the limit does not exist. Right? So if I did this, and say that's 3 to the x, we'd say that limit does not exist. It just goes to bigger and bigger and bigger to infinity. And of course, when this happens, we call it diverging. That's the opposite of the converging. It's diverging. All this stuff we've seen before. It should be familiar. If not, it's just a good little brush up on our terms. And remember, does not exist usually means it goes to or towards infinity or negative infinity. Because for it to be a limit, it has to be an actual number, which infinity is not a number. It's like a concept of just infinitely big or infinitely small, but not an exact point on a number line, right? So we can't say it's an actual limit. So we already saw this before, where this is the golden rule when it comes to limits with polynomials, right? And we want to understand this and not memorize it. So review this. If we want x to get infinitely large and it's on the denominator, what happens to the overall number, this whole number, as x gets really, 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 really big? All right, so if you just do 1 over 1, 1 over 2, that's 0.5, 1 over 3, 0.3, 1 over 4, 0.25, you already kind of see it gets smaller, smaller, smaller. So as soon as you get to 1 over a billion, well, that's basically equal to 0, right? So we understand why this is true and not just memorize it. So this is the trick we use for a lot of the limits, right? And this one a little bit also. K is just a regular number, so let's say if I had like 8, right? That's the equation y equals 8, and that would be right here. So, well, what's the limit of this function? Well, it's not going up or down. It's already converged. It's every single point it's at 8. That's why the limit equals 8. So this only applies to when we have no variables and just a number, right? But sometimes straightforward problems like this, if you don't know what the question is, you're not sure what to put. I think that was on the quiz when we did sequences, and there's still some people that missed it because they're not understanding what the limit or the graph looks like. They're trying to memorize it. So let's do this by conceptual so it actually makes sense and not memorize things. Now, back over here, this applies to pretty much anything. So when you come to a new problem, you say, well, what if there's a 2 here? Is this still true? Does 1 over 2 times like a zillion, is that still 0 basically? Yeah. What if I had put a 4 on top? Yeah. So it's not just 1 over x, it's any derivative of it. Like any number, if I put 1 over x squared, right, that goes to 0 even faster, right? So you want to look at this not just as 1 over x, but all the derivations. This is some coefficients and things like that. Right? And know that applies to it well. And if this is like a squared, it gets there even faster, right? So, yeah. So keep that in mind as we're doing this. So what we're going to do is the same thing we did before, right, with these types of problems. Right? We are going to go through and divide everything by the largest coefficient, right? So we look at this and say, so 3 minus x, and I leave a little space because I'm going to divide underneath it, and x plus 1 underneath, and then go through and look at what is the largest degree. In this case, it's 1, or just x, right? X to the 1 power, and divide everything by that. Right? So, and simplify. Next step is just to simplify all this, whatever you can. Still writing this part. And we just simplify these one at a time. So we have 3 over x, which can't be simplified. So I just rewrite 3 over x. And then x over x, of course, equals 1, so minus 1. And do the same thing on the bottom. X divided by x is positive 1. And then 1 over x does not simplify. So this is like the setup for taking the limit. And at this point, we're actually going to take the limit. So we're going to pretend, what if x gets infinitely large, right? So 3 over x, that's basically the same as this. 1 over x, 3 over x. This part will go to 0. Right? Then we'll have minus 1. Right, we're just taking the limit of anything that has a variable. And then, of course, 1 over x will go to 0 as well. So this just equals negative 1 divided by 1, which is negative 1. And it's really important for your work that you note that right here I still have this part written. And then once I start doing the replacing with the 3 over x with 0, that's called taking the limit. That's why this right here equals 0, right? So I'm replacing anything, a limit of anything of this nature with a 0. So that's why this part is not written anymore. And it's important to know that and write it when you're supposed to, and then not write it when you're not supposed to. So pay attention to that part as well. Of anytime these zeros start appearing, that's when this thing is no longer written, because you've technically taken the limit. All right. All right, so try that with number 1. Give that a go. Showing all the work, all the steps. Check with one another. All right, so we should come up with the answer of 2/3. And like I said, the only thing that can really get you in trouble grading-wise is if you didn't write this. If you did your own shortened version that doesn't include any of this, you just don't do that. So just assume you're a new employee, the boss is telling you, here's the job, here's exactly how to do it. I don't want you to think about it. I don't want you to think about what your opinion is how to do the job. If you're being hired to do this job, do it exactly how you've been shown to, right? It can get you in trouble down the road, so I'm just trying to get you to have good practices, so not starting things lazy when doing things. Well, I can get 2/3 without writing that, so I'm going to, no. Don't do that to yourself. You'll do a lot of work, and unfortunately when AP testing comes around, when you don't know how to show this and write it down, you start getting dinged on problem after problem after problem because you've made up your own calculus instead of learning it, the way it is. And if you get to higher classes, you realize why things have to be a certain way, and you can't just, leave things off because it's inconvenient or because it's a little more writing. All right, so we want to do things correct from the beginning. All right, so we got some basic rational functions. No problem. We've done these before. Let's go to square roots. And there's going to be 2 types of square roots. One with the square root around everything, which we're really not going to change pretty much anything. And then we have a different little trick we have to use when there's a square root only on the top or bottom. So pay attention on your homework which ones have that, because it is a little bit different from the others. But for this, you could probably go through and do the same things we just were doing and do just fine. Right? So follow the same steps. So I'm still going to divide by the largest degree. Which is x squared. Don't forget to keep that square root there, rather large. There you go. And it should be over everything, top and bottom. And keep it going, reduce everything. So we get 4 plus 3 over x, and 1, and 1 over x squared, square root everything. Then we can take the limit. Plus 0, 1 plus 0, square root everything. So our answer is just 2. And I mentioned there's only one thing different, and that is at the end we had to take a square root of everything, the whole rational expression. But all in all, basically the same thing. So most of your functions will be rational, a lot of x's and polynomials on numerators and denominators, right? But you might come across, as you saw in previous homeworks, things with, randomly will be a trig function or a log function. So you might have to reach back and just kind of remember, what happens with these types of functions. Particularly, so if you're taking the limit, just like we just did here, take the limit of anything that's in this format, right? So that will just equal 0. So we didn't have to do a lot of setup and dividing or anything. This is already set up to 1 over x, so we're already basically at this stage where we can just substitute in 0 for anything of that format. And of course, what's the cosine of 0? 1. So you can get an answer. Now you have to put those together because, all of a sudden we're doing trig instead of polynomials, so you have to bounce back and forth to all the rules of all the functions that we've worked with all year long, right? Whether it's sequences or trig or even imaginary numbers if we got to it. All right, so we can still handle these, and often the answer or explanations is a lot shorter. Now, if you're not sure about everything, graph it. You guys had the benefit of Desmos. You could actually look at the graphs of all these. If you got to that and you're saying, "Oh, I didn't know what to do," which is an obvious point when you're doing mathematics. You might come to something like, "I don't know what that is," which is fine, right? But what's not fine is saying, "Well, I didn't know what to do, so I did nothing," or "I waited to ask somebody else." You do the work. You pull up Desmos, you graph it, right? And then you can see right away, as we get to infinity, this thing just, we don't even care about what's happening at 0, right? It's what's happening way down here, and you can see, oh yeah, that goes to positive 1, both on the right-hand side and the left-hand side. So you can see what the answer is without, with rather little effort, and you can figure out what these answers are if you happen to get stuck or are not sure, right? Always can just check your work very quickly. All right, so lastly, this is when I mentioned that you might have to do something different, okay, because of the square root. And I'll show you what the issue is here. Oops. Scoot over. Go away. There we go. There we go. So here's the issue here, is that if we go through the same steps, right, and we usually divide by the highest degree, which would be the same as if we multiplied by 1 over x squared and then distribute that in, right? That's the same way as dividing. We usually go straight to dividing, but technically what you're doing is multiplying by 1 over. But for this problem, I'm going to multiply by 1 over x squared instead of just dividing, because when we have one part that's in a square root and one that's not, we get a little issue that pops up. So I'm going to multiply top and bottom of this one by 1 over x squared. So on the bottom, right, I'll basically get x squared over x squared when I distribute this through, and I'll get minus 3 over x squared. So more or less, I'm just distributing this times this times this, with no problems whatsoever. Let me correct myself before I get too far here. I still haven't taken the limit, so this part I have to write in. Not till I take the limit does that disappear. All right, but what about the top? What is root x squared plus 2 times 1 over x squared? So if we know our rules for exponents, if I have like a square root, that's like times 3, and then a non-square root times 2, well, what does this multiply to? That's just 2 root 3, right? I can't combine them because they are not both in a square root. Whereas if this was a square root, like root 2, now I can actually combine those into the same radical. So I need to have a square root on this. But the problem is I can't just go randomly say, well, I'm just going to put a square root there because I need it. Because now this isn't equal, right? The top and bottom are not equal to one another. So what I can do to counter that square root, though, is just square the inside. And now it's still equal to 1 over x squared, right? It's just the square root of a square, so we're okay here. And now I have a square root there, and now I can actually combine these together, right? So it's a little trick algebraically to get things to work. I only have to do it on the top with the radical. The bottom, you notice, is just the same old, same old. So little problem you're going to have to look after here. Now, what is 1 over x squared squared? Yeah, so this part is going to turn into, all right, we'll still have x squared plus 2, but instead we're going to be dividing by x to the 4th, which is 1 over x squared squared. So make sure you make that connection on why this is x to the 4th instead of x squared like the bottom. And don't forget, we still have the square root there. So the whole reason we did all this work is because of the square root. So don't forget to leave that part in. So now we can simplify everything. All right, x squared over x to the 4th. 1 over x squared. And then 2 over x to the 4th. I can't simplify that. But on the bottom I have x squared over x squared, which is 1, minus 3 over x squared. So here I can finally take the limit, right? So I'm going to get 0 plus 0. Oh, I forgot the square root. All divided by 1 minus 0. Which equals just 0. So you notice, looking at the original question for all these, if I go back and look at the beginning, you might have looked at this one and say, well, if I wrote this as negative x plus 3 instead of x minus 3 and just reverse those, and then the top here is just x plus 1, when you're dealing with infinity, you might look at it and say, well, infinity, negative infinity plus 3, that plus 3 really doesn't change negative infinity. Same thing here. If I plug infinity and I add 1, well, that's really the same thing. And then I could look at this and say, well, x and x cancel out, so my answer is negative 1, which that is the answer. Same thing over here. I could say, well, if I'm squaring infinity, adding 5 times infinity really doesn't change it. Neither does subtracting 1. And if I look at this, well, infinity squared divided by the same infinity squared, those would cancel out. And now I get 2 over 3, which does work for these simple problems. But if you keep doing that, saying, well, I don't need to write it down, and then by the time you get to here and you stare at it, you're like, yeah, you're probably not going to figure out that it's 0 by looking at this. So, yeah, there is some shortcuts to take in the beginning, but definitely still show the work because it's going to get more difficult, especially when you get to trig. It's not going to be intuitive at all. We have to do all this writing just to make sure all our calculations are correct. All right, so you guys have time to work on this. Look at all the problems. Categorize which ones are more like A and 1 and which ones are more like C, where you have to do more work. And try to get those problems done before you get out of here, right? Save the easier ones for later on. All right, let's get to work.